Hello, hello. Okay. Hi everybody. My name is Yanis. I'm a developer and working at PSC and Ethereum Foundation. PSC is a R&D lab focused on privacy within the Ethereum Foundation. We have many projects. I invite you to visit psc.dev to see all of them, and also Cursive, who has firstly designed the scheme I'm going to present. So big shout out to them. So I wanted to start with like just do a kind of a picture of the situation right now, where we are with importing Web2 data with ZK and building all these credentials. So today in 2025, it's possible to prove some statement from your email box. We have all these ID wrappers, Anonadar, ZK Passport, Self, that allows users to prove a statement from their identity document. We have the TLS provers, and any types of signature we know at the moment how to snarkify them and prove a statement from that. So the next question is like, okay, so now that we are at this stage, like, what can we do with all this data? So the first intuition that when you encounter this type of systems is to build authentication mechanisms. So if you can prove to me that you're more than 18, or if you can prove to me that you're from a specific area, then you can log in. So it's a very interesting logic, but if it's the only thing that we propose, in the end, we will still fit the same power structure. And also, authentication mechanism and like throwing these proofs to a third party has like a lot of issue in terms of export. So just this small schema so as soon as you snarkified some signed data and you generate a ZK proof of it, then there are a lot of whole field working on, okay, what should be the export format? What should be a standard for this type of credential to be presented? Another thing that we can do with this type of credentials is actually do selective disclosure and decentralized verifiers. So we can send these proofs to the chain and verify some statement about it. So this still have a lack of privacy because, like, even with selective disclosure, you still have to disclose some information. So if you're more than 18, then you will have to say to the public network that you're more than 18, and you will have like your proof linked to your address. So Trinity started like with a reflection. I mean, the work on Trinity started with a reflection like about like what would be like a more cypherpunk approach to these with these ZK credentials. So this type of artifacts like let us like prove cryptographically that we own some information from a trusted issuer. And what they should enable is like privately interact and create a trustless layer where we can compute over our private data. So that's where MPC enters in the picture. So basically, MPC enables you to evaluate f of A, B, and so A is Alice and B is the input of Bob. So Bob never learns A, Alice never learns B, but they can learn C, the output of their computation. So yeah, just basically like an intuition is that instead of proving statement and throwing it to already established mechanism, like Airbnb, for example, we should use actually these artifacts to think about systems where we can bypass decentralized actors and actually like create system where we can organize ourselves and create meaningful exchanges and economic exchange. So the problem statement that we're trying to solve is the following. So Alice and Bob, they want to know who is going to pay for the dinner tonight. And the rules are the following. So the wealthiest is going to pay for the dinner. And they want to keep their wealth private. So the solution to that problem is actually Boolean circuits and garbled circuits. So that's a work from Yao's end of the 80s, beginning of the 90s. So that's since a pretty long time we know how to solve this problem. So I'm just going to do a quick primer. Like I'm going to be short on it, but just to give some intuition. So basically, when two parties want to evaluate a private function, they have to build these Boolean circuits, and they have to assign labels. And basically, they want to exchange labels in the way that none of them will learn the input of each other. And so you need to perform like what we call like this oblivious transfers. So again, the goal of this presentation is not to understand all the math behind it, but it's just like to give some intuition about like why the construction from Trinity and from the paper is actually interesting. Yeah, so the thing is that they have to use public key most of the time, public key encryption, and so public key encryption lets you encrypt a message toward a public key. So basically, in that exchange, they will know each other's public key, and they could exchange some bits to perform the evaluation of that circuit. So in a classical OT way, you would have like to perform like this exchange like bit by bit and perform like oblivious transfers bit by bit. So a big breakthrough that is an enabler for Trinity is this paper, extractable witness encryption for KZG commitments, and so the main enabler of this paper is it's not yet witness encryption. So witness encryption is like kind of a holy grail in cryptography that we haven't achieved yet. It's basically the idea that you can encrypt like a message toward a puzzle, and if someone has the solution to that puzzle, he would be able to decrypt the message. And so what they built in that paper is what they call extractable witness encryption. So it's not about just proving that you know a solution for that puzzle. It's also to prove a statement about this specific puzzle. And so in that case, so KZG is a polynomial commitment scheme. So in a polynomial, you must prove that you know at a specific value, you know the opening value. And so here, like in this scheme, it's not just about knowing the opening value, it's also being able to prove that you know the original polynomial that resolves at this specific value. So the main intuition here is that why I'm speaking about all of this is just that, so this enables like what we call laconic oblivious transfers. And basically like in the previous scheme that I showed you, we have like to exchange, like to communicate for all the bits that we have to exchange. But with laconic oblivious transfers, we can commit to dictionaries, and we can turn a protocol that is like a multi-round of communications to actually run one round of communication. So okay, so that's the first property that we demonstrate to solve our Alice and Bob problems. So now in a Yao's problem, so we solve one first problem is that we can have like a 1-2 round 2PC protocol where Alice can commit to her input. Bob can garble a circuit, send the labels through this oblivious transfer, send back the garbled data, and then Alice can evaluate and know who is going to pay for the dinner tonight. So now, how does it relate with the introduction with ZK? So that's basically like what Trinity is trying to achieve. It's an efficient way to do two-party computing, and on top of that, we plugged Plonk, which gives a very nice feature, which enables like the verification of the inputs of our two participants. So in the case of Yao's billionaire problem, when Yao's designed the circuits, there were no assumption about like the input I'm going to insert into the circuit. So basically, I can spoof my wealth and say that I have like a lower wealth than I have because I want a free dinner. And it's called Trinity because it assembles like three notions. So two that we just introduced, garbled circuits and extractable witness encryption. And now I'm going to present like how we plug the Plonk into the picture. So Plonk has like this table arithmetization, and so again, it might be overwhelming for some people. But just the intuition I want you to get is just that. So in the arithmetization, you have these columns, and so you can basically throw any computation to the prover and just say, okay, so use all the columns to perform like different checks on the data that I'm going to insert into the circuit, but just reserve one column to actually the input I want to commit to the 2PC process. And so basically we would have like one column with all the columns are committed with KZG. And so again, that's how it's the glue between like the paper about extractable witness encryption and ZK that we were able to achieve with Trinity. So basically now we have a scheme that where you can generate a Plonk proof that is verifying any statement that you want. And inside of the prover, you can reserve like a specific column to say, okay, that is going to be my input to the 2PC protocol. So Alice and Bob, they live in a wonderful country, which is France, and their tax report is actually signed with ECDSA. So they are able to prove their revenu fiscal de référence, and they are able to actually like insert the public key of the government, the message that has been signed, and the signature into a circuit. The Plonk prover is going to check the signature of this data, attest that in fact there is like a well-formed data that was signed by the government without revealing anything that was signed. And what we're going to do is just we're going to extract the wealth, insert it inside our dedicated column, and then so we will have like a Plonk proof that a prover checked the authenticity of that document. And inside of this proof, we will have like our commitment that we are going to use in our 2PC protocol. So what we've just built, sorry, it was a bit fast, but just that is the full picture of what Trinity could enable. So basically, you can have two parties. They have a provable statement and a provable piece of data. They can generate both on their side a proof. They can commit to that proof like on a public network such as Ethereum. So the thing is that these proofs and commitment, they are very short. So that's one of the main property of this polynomial commitment scheme that is KZG is that the commitments are really short, and so to publish them on a network such as Ethereum is like very cheap. So they can post a proof, so you have decentralized verifier, and there is no notion of selective disclosure because like the thing that you're going to disclose is obfuscated inside of the commitment, and basically only this information will only be used inside of the Boolean circuits, and there are no way to learn anything from the commitment and the proof that was posted in the smart contract. Only them, by communicating, they will be able to evaluate a function based on these proofs and commitment. So Alice is going to generate a proof, post it on chain. Bob just has to get the commitment from that published proof. So he cannot see anything about the wealth of Alice. He can just see that, in fact, the verifier that is verifying the French tax report signature has been checked and get the commitment, garble a circuit. So garbling a circuit, he can like choose any circuit that he wants. So in that case, they would have to agree on a circuit that is performing who's the wealthiest. And he can also, like on his side as a garbler, insert his inputs without Alice learning anything about his inputs. He can set back this garbled data, and then Alice can evaluate. So what we just built is that it's a computation layer over ZK SNARK that is only like we can say one round. Why we can say one round? Because Alice's proof, as soon as it's posted, anybody can interact with it. So not only Bob, but anybody can show up, get this commitment, and garble a circuit with it. So we can consider that this first part where Alice has to prove can be for free because like she will post it, and then from that she can enable like many interactions with many people in a private way with 2PC. So what it enables, there are a lot of things that Trinity can tackle. I'm going to focus on the most interesting ones. Key management. So Trinity could be a way to actually obfuscate some signing mechanisms. So basically, you can commit to some form of message that you want to sign, and the inside of the 2PC circuit, the garbler can insert some logic, such as like if true, then sign, if not sign. And so basically, you can have like this mechanism where they can both perform a signature together based on like obfuscated logic. I think also Trinity might be very suited to marketplaces. So basically, like if you think about it, if you have ZK email and you can prove the ownership of a digital item, then you can post that proof, and someone can and as it's reusable, you can use that proof as a way to have private list on chain. People can get that data, fetch that data, insert some private auction or private way to agree on a deal, and then like the evaluator can learn the result, and then they can perform a transaction. I think it's also very interesting, like basically everything that has like a matching logic, a job marketplace where you can, for example, commit to in a provable way to your track record or your curriculum, and a potential employer can interact with it. That's also a very nice use case, and just basically credential matching. So you wanna make sure that the person you're interacting with is from a specific area, or like is more than 18, for example. You would be able to do it in a more private way without the other party having to actually like post the data. Yes. So in conclusion, like we think that Trinity is enabling real peer-to-peer application where trust and disclosure are not needed. Yeah, so that's a very interesting project. For now, we are just at the phase where we delivered like a first implementation, and we are thinking about like use cases to tackle. So if you have any interest in Trinity, please reach out to us. Yes, again, thanks to all the people that make this project possible. And here it's the link to access the GitHub repository and my contact if you have any questions.
Does anyone have a question?
Thank you very much for the very interesting talk. I have a question regarding the performance of or the cost basically for the prover side. Do you do already some preliminary benchmarking on how costly it is?
Yes. So in fact, Trinity has two modes. So I presented the mode like with the ZK assumption, where you want to have like a strong trust assumption on the input. And in that case, like the benchmark will be basically the same benchmark as a Hello2 prover. So there is no like extra cost to adding this extra advice column. So that's are basically the same. So unfortunately, Hello2 has not the best performance, mainly in terms of memory. But the intuition is that as faster provers also use KZG, and the first one I have in mind is Bartenberg, for example, from Aztec. You could, for example, replicate the same logic with a faster prover.
Thank you.
Anyone else? So thank you so much for your presentation.
Thank you.